Okay, now let's take a look at related rates. Related rates problems are problems where you have some description. It's often a formula, a known formula like the area or volume of an object or the Pythagorean theorem. So you have some known description, which comes out of word problems that we'll do in a few minutes. But to set up the general mechanics of how we compute related rates, let's suppose that the formula we know has been described as y equals f of x. So x may represent some known quantity like a radius or a length or something like that, but perhaps this quantity x is changing over time. So we can view x as a function of time. So f is depending on x, but x may be changing over time. So implicitly f depends on t. If t changes, then x changes, which means f changes. So what is df dt? Well, we have here a chain rule construction. So we have f of x of t, but I want to present this a couple of different ways because the different ways that we present it will emerge when we do related rates calculations. So on the one hand, df dt is d dt of the composition f of x of t. That's what df dt is. And then by the chain rule, we could compute that as f prime of x of t, where here I'm using Lagrange notation. So that's derivative of the outside function evaluated at the inside function times the derivative of the inside function. And now let me write that that's f prime of x times x prime of t. But here, the Lagrange notation is a bit dangerous because prime is ambiguous. So this first derivative, f prime of x, is really df dx, whereas x prime of t is dx dt. So this is another way to express the chain rule that is easier to state with Leibniz notation. In this context, where we have f depending on x depending on t, df dt is df dx times dx dt. You have to be careful here because these are not fractions. This is not df divided by dx times dx divided by dt. Sometimes students look at that and they say, oh, that's obviously true because the dx's cancel, but that is not fractions. This is a rate of change. Okay, it's not clear here that I have two approaches, but when I wrote d dt of f of x of t, the idea was that I plugged x of t into f so that all I'm really left with is a function of t. Whereas the chain rule, as we've expressed it with Leibniz notation, is really like you can leave df dx as is and then times dx dt. So you might be mixing x's and t's there. Let's see how this manifests itself in this first example. And I should remark here that we haven't really started related rates. This is kind of a warm-up. So suppose that f of x is sine of x and x of t is t cubed plus 1. So f depends on x and x depends on t. Compute the rate of change of f with respect to t. So method 1 was really like take x of t and plug it directly into f. Then we differentiate with respect to t. Well, f of x of t is sine of t cubed plus 1. When you look at that expression on the right, all you see now is t. So df dt is d dt of that expression. So that's d dt of sine of t cubed plus 1. And just by the regular old chain rule, that's cosine of t cubed plus 1 times 3t squared. Method 2, using the chain rule, we can write df dt is df dx times dx dt. So df dt is df dx times dx dt, where I'm going to compute each of these individually. df dx is just the derivative of sine x with respect to x, that's cosine of x, times dx dt is 3t squared. So that's cosine of x times 3t squared, and then I can plug in t cubed plus 1 for x. So that's cosine of t cubed plus 1 all times 3t squared. And then you see, of course, that's the same derivative that we got with method 1. Often, we may not know how the measured quantity x depends on t as a function in general, but we do know its instantaneous rate of change, at least at a particular moment where we're interested in our formula. So suppose f of x equals x squared plus cosine of x is some formula that we're studying. And while I don't know how x of t behaves in general, I do know that at a certain moment in time, let's just call that t naught for now, dx dt is 10. So the rate of change of x with respect to time is 10. We would like to compute df dt at that one particular moment, and when I wrote this problem, I forgot to mention that you also need to know the measurement at that moment. Okay, now what I called method 1 on the previous slide isn't going to work because I can't plug x of t into f. We don't know what x of t is. So we have to go immediately to method 2. df dt is df dx times dx dt. df dx is 2x minus sine of x. And then dx dt we know is 10, even though we didn't know what x of t was as a function. Now here, I'm being a little bit careless because at a particular moment, dx dt is 10. That might not be true in general. So it's important to emphasize that this is one moment in time, and I really should go ahead and plug x naught in for our x value because that's the x value when dx dt is 10. So at t naught, df dt is 20x naught minus 10 times sine of x naught. So that's df dt at one particular moment in time. This is often the case with related rates. You're given a rate of change, but you're not given a broader function. So we might know the analogous information to knowing dx dt without knowing x of t. Because of that, I think a new viewpoint is useful. I'll call this method 3 for now, but it's really just another way of telling the same story. So given our formula, f equals x squared plus cosine of x, we're going to implicitly view f and x as depending on t. So even though t doesn't make an appearance in this equation, let's differentiate everything with respect to t. On the left-hand side, I have df dt. On the right-hand side, I have 2x dx dt minus sine of x dx dt, where for each of those, I was doing the chain rule, so it was really x of t squared and cosine of x of t. So at the one particular moment we're interested in, t naught, the rate of change of f with respect to t can be measured as 2 times the quantity x naught times 10 minus sine of x naught times 10. And of course, that's the same thing as the line above. Sometimes you might have multiple quantities depending on time. Even in a single variable calculus, you could actually have multiple inputs appear in a related rates problem. So let's look at, say, the volume of a circular cylinder, which is pi r squared times h. R is the radius of the cylinder and h is the height. Now let's suppose this cylinder is somehow expanding over time. So its radius is expanding, its height is expanding. As the radius and the height grow, the volume must be expanding. And in particular, suppose that we know right at the moment when the radius is 4 and the height is 2, that dr dt is 1 and dh dt is 5. So those might not be the rates of change of the radius and the height with respect to time in general, but at some particular moment in time, those are the two rates of changes that we're measuring. So at that one particular moment, compute the rate of change of volume with respect to time. Now here, v depends on r and h. So this is actually a multivariable problem, but it's okay, we can still do it. What we're going to do is take this equation and differentiate everything with respect to t, where here the volume, radius, and height are all changing over time. So they are all functions which are depending implicitly on time. On the left-hand side, we have dv dt, and on the right-hand side, I have pi r squared h. Pi, of course, is just a constant, and with r squared h, we're going to use the product rule. Each of them is implicitly a function of t, so when I do the product rule, every time I take a derivative, it's going to be the chain rule. So let's start with our first term in the product rule. It's going to be pi, the derivative of r squared, then times h. So that's pi times 2r dr dt times h. And then for the second term in the product rule, that's pi times r squared times the derivative of h. So that's going to be pi times r squared times 1 times dh dt. So again, this right-hand side was a combination of the product rule and the chain rule. So at the particular moment that we're interested in, we can plug in our known measurements. dv dt is going to be 2 pi times the known radius of 4 times the known dr dt value of 1 times the known height of 2, and then plus pi times 4 squared times dh dt at that moment we know to be 5. Okay, then we add all that up, and I believe we're going to get 96 pi. So the volume is growing at a rate of 96 pi units cubed per time measurement at that one particular moment in time. Because this follows the same pattern above where we just go through and we differentiate every quantity that depends on time with respect to time, it often doesn't feel like it's a different kind of problem, but technically volume here is a function of two variables, r and h. So I'll mention here the multivariable chain rule. It's just an aside, an extra piece of information. If you have a function of the form v of r and h, so two inputs, v depends on r and h, and then each of those individually depends on t, the multivariable chain rule, which you can check, will give you the same result as the above, is dv dt is dv dr times dr dt plus dv dh times dh dt. Now you have to be a bit familiar here with partial differentiation to test this formula. In particular, those funny d's I wrote for dv dr and dv dh are what we call partial derivatives. So if you've seen that before, you can check this formula, but if not, it's not a big deal. Again, you just take the expression you have and go through and differentiate everything with respect to t. Okay, now let's look at some word problems. If the radius of a circle is increasing at the rate of 2 inches per second, how fast is the area of the circle changing when the radius reaches 12 inches? So we identify the formula that is going to be useful for us, and that's area of a circle is pi r squared. And then I typically like to identify what pieces of information we already know. So at the moment we are interested in, the radius is 12 inches, and dr dt, the rate of change of the radius with respect to time, is 2 inches per second. Now, following the train of thought of method 3, as I called it a minute ago, let's differentiate the equation a equals pi r squared with respect to t. So here pi is a constant, but r and a, the radius and the area, are changing as time changes. So each of them is a function of t. On the left-hand side, we have dA dt, and then on the right-hand side, it's r of t squared. So using the chain rule, we get pi times 2r times dr dt. Then at the moment when the radius is 12 inches, dA dt is 2 times pi times 12 for the radius times 2 inches per second for dr dt. And so we get that the rate of change of area with respect to time at that one particular moment is 48 pi inches squared per second. Okay, for our next example, we have a ladder which is 10 feet long and it's propped up against a wall, but it's sliding down. If the height of the ladder on the wall is changing at a rate of 1 foot per minute, then how fast is the bottom of the ladder sliding away from the wall? And once again, I've forgotten to give you every condition you need. So let's set this problem up so that we're computing how fast the bottom of the ladder is sliding away from the wall when the height on the wall is exactly 8 feet. Okay, so here's a Desmos graph showing what's happening. We have a ladder propped up against the wall, and the moment we're interested in is when the ladder is 8 feet high on the wall. The ladder is a constant 10 feet, so if the ladder were all the way against the wall, it'd be 10 feet tall, but it's sliding down. And if it kept sliding down, eventually it would just land on the ground. So looking at this, I would notice that we have a right triangle every moment when the ladder is sliding down. The hypotenuse of this triangle is a constant 10 feet, so that's not changing. However, the height on the wall and the distance from the base of the ladder to the wall, the two legs of the right triangle, are changing. So I don't want to set those to be a constant or anything like that. I have to remember that they're changing over time. So let's set the height on the wall to be h. That is a changing quantity, and its rate of change with respect to time is dh dt, which is -1. Notice we have to give it a negative sign because this ladder is sliding down, so h is decreasing as the ladder slides. At the moment we're interested in, h will be 8. Let's call the length of the leg on the ground x. That is also changing over time. And if you reread this question, how fast is the bottom of the ladder sliding away from the wall? Then what we're looking to solve for is dx dt, the rate of change of this length on the ground with respect to time. We need x at the moment we're interested in, which is when the height on the wall is 8. On the previous problem, our useful formula was the area of a circle. Here, the useful formula is going to be the Pythagorean theorem, x squared plus h squared equals a constant 10 squared. At the moment we're interested in, x squared is 100 minus 8 squared, which is 36. So the value of x at the exact moment when we're going to compute dx dt is 6. Now we want to go through and differentiate every quantity in our useful formula with respect to time, where here x depends on t, h depends on t, and of course the length of the ladder does not depend on t because that's just a constant 10. Okay, so if we differentiate implicitly with respect to time, we get 2x dx dt from the chain rule plus 2h dh dt, also from the chain rule, equals 0. Now we can plug in for x and h. X is 6, h is 8, dh dt is -1, and that leaves us with one unknown quantity, dx dt, which we can now solve for, and we get dx dt is 4/3 feet per minute. It makes sense that that's positive because as our ladder slides down, x is going to grow. It started, let's say if the ladder was against the wall, it started at 0, and when this ladder is done sliding, it will be 10. So this quantity is growing. So you always want to step back, especially to look at the sign of the derivative you've computed and decide geometrically and physically if that makes sense. Okay, let's take a look at our final example of a related rates problem. And this is going to be another geometry problem. It's going to be a volume problem. And I chose this one because this is an example of a formula which has two variables. So water is dripping out of a tank shaped like a circular cone at a rate of 0.5 meters cubed per minute. It's meters cubed because it's volume. Overall, the tank is 16 meters tall and 4 meters wide. So we understand here we're going to work with volume, and the volume of a circular cone is pi thirds r squared h. So if we have water in this tank at a certain height, our way of computing the volume depends on both r and h. But the tank is not necessarily full. In fact, water is dripping out of the bottom. And however high the water is, we would compute its volume by knowing the radius at the top of the water and the height of the water. Actually, I want to use little r and little h for that. So let me call the radius of the circle capital R and the height capital H. Okay, then as this water drains out of the bottom, the radius at the top of the water is going to be changing because the water is going down, so the radius is shrinking. So let's call this little r of t, and likewise we'll call the height of the water at any moment in time little h of t. Okay, ultimately we're going to work with the volume of the circular cone as our useful formula, but we have another important relation here that's going to help us solve this problem. And that is that if you look at say, the right triangle you make from the central axis of this cone over to the side of the cone, we see similar triangles emerge. The ratio we get from that is the radius of the water to the height of the water at any moment in time is going to be equal to 4/16, the radius of the tank to the height of the tank. This gives us a relation between our two variables. So h of t is always going to be 4r of t. And this is actually an important formula just relating h and r. I could differentiate both sides with respect to t, and this tells us that at any moment in time, dh dt is 4 dr dt. Okay, now let's go ahead and differentiate our volume formula with respect to time. Here, volume, radius, and height all depend on time. Pi over 3, of course, is a constant. So we'll have dv dt equals pi thirds, and then to differentiate r squared h with respect to time, we're going to use the product rule. So differentiating the first term, that's 2r dr dt, and then times h, plus pi thirds r squared dh dt. We know that dv dt is negative 1/2 because the volume is decreasing at a rate of 0.5 meters cubed per minute. Okay, so now let's look at this formula and the questions we're asked. We're asked to find how fast the radius of the water is shrinking at a certain moment of time, so that's dr dt. And then we also want to know how fast the level of the water is lowering at the same moment in time, but that's dh dt. Okay, so in this formula, dr dt and dh dt are what we're going to solve for, so it's okay that those are unknown, but we do need to know r and h. So the next step, and you could have done this first actually, is to find r, the radius, if the volume is 36 pi. That's the moment we're interested in. So volume is 36 pi. Plugging that into our formula, we get that that must be pi thirds r squared. And then instead of h, I'm going to write 4r based on the similar triangles calculation we did on the left. Now I can divide 36 by 4. That gives me 9 times 3 is 27. So we get r cubed is 27, or in other words, r is 3. That also tells us simultaneously that h is 4 times 3, so it's 12. Okay, returning to our formula, we now have negative 1/2 is pi thirds 2 times the r value of 3 times the unknown dr dt times the h value of 12 plus r squared, so 3 squared, times, and then in the formula we have dh dt, but I'm going to replace that with 4 dr dt. Now simplify that, right-hand side, you get pi thirds times 108 times the unknown quantity dr dt. We can now solve for dr dt and say that dr dt is negative 1/2 divided by pi thirds 108, which is 36 pi. And after simplification, you get that the radius is shrinking at 1/72 pi. In other words, dr dt is negative 1/72 pi meters per minute. Now to answer the second question, we could start the problem over from scratch, or I could go up to dv dt and convert r's into h's, but there's a faster way. It's better to use our formula in the bottom left relating dh dt to dr dt, which we now know. So dh dt is 4 dr dt. So at the moment we're interested in, it's 4 times negative 1/72 pi. Therefore, dh dt is negative 1/18 pi meters per minute. Notice both dr dt and dh dt are negative because as the water drains out of the tank, they're shrinking. Volume is a three-dimensional measurement here, so it makes sense to say dv dt is meters cubed per minute, whereas r and h are one-dimensional measurements, so dr dt and dh dt are meters per minute. Okay, so this was our last example of a related rates problem. Thank you for your attention.